As electrons flow through a conducting material, their flow is impeded by the attractive and repulsive forces that are acting between the atoms of that material and the electrons. Different materials impede the flow of electrons to different extents, and this property is known as the resistance or resistivity of the material. Before we really get into this, we want to clarify a couple terms. We discussed resistance before and how it relates to the voltage and current of a circuit. Resistance is the electrical quantity that measures how a device or material reduces the electric current flowing through it. It is given the designation of capital R and labeled in ohms. Resistance comes from the electrical interactions between the flow of electrons and the atoms that make up the conducting material. So as an electron flows through a material, its progress is affected by the attraction and repulsion of the protons and electrons. The resistivity of a material is designated by the Greek letter ρ and is a constant of proportionality that describes the ability of the conducting material to impede the flow of electrons. The more an electron is attracted to an atom of a conducting material, the more difficult it will be for it to move through the material. When a material acts to slow down the flow of electrons, it is said to have a high resistivity. There are several properties of a material that will determine the total resistance within a circuit. The first is the material itself. This is described by the resistivity, which is actually a constant specific to a certain material. The values will depend somewhat on purity, heat treatment, temperature, and other factors, but in general, this is a constant value we can look up. The length of the material simply describes the distance the electrons must flow. The longer the distance, the higher the resistance. This makes sense since the electrons will need to travel through more of the atoms of the conducting material. The area is the cross-sectional area of the material with respect to the direction of the current flow. Resistance is inversely proportional to the area, since a larger area would mean the electron has more space to move around and avoid any impeding atoms. We can put all of these variables together into an expression that describes the resistance is equal to the resistivity times the length of the material divided by the cross-sectional area of the material. Materials can be classified based on their resistivity. Conductors are materials that allow electrons to easily flow through them, and they are materials that have a very low resistivity. Silver, for example, has a low resistivity and therefore is the best conductor. Copper is close and much less expensive, which is why it's so commonly used in electrical wires. Aluminum has a pretty high resistivity compared to copper, but since it has a much lower density, it can be used more efficiently in some situations where weight conservation is a concern. Materials that have a high resistivity are referred to as insulators. These are the substances that we use when we do not want the electric current to flow in some direction. For example, electrical wiring is often surrounded by hard rubber in order to keep current moving where we want it to go. And then there are semiconductors, which are materials that allow electrons to move through them under some conditions, but not others. This makes them a good medium for the control of electrical current. So say we want to find the length of an alloy wire with a resistivity of 5.0 times 10 to the negative 7th ohm meters. It has a diameter of 0.5 millimeters, and it is required to make a standard 6.0 resistor. Here we are looking for the length of the wire. When we look at our equation, we probably immediately notice that it does not include a variable for the area. It is fairly common for wire to be marked according to its diameter, and with a little math, it is a simple matter to find the area. Then we can rearrange our resistance equation to solve for the length, since we know all of the other variables. We find that we need 2.4 meters of wire. So suppose you want to connect a stereo to a set of speakers. If each wire must be 20 meters long, what diameter copper wire should you use to keep the resistance less than 0.1 ohms per wire? Here we are looking for the diameter of the wire. Now again, when we look at our equation, we probably notice that it does not include a variable for diameter. However, we can assume that our wire is probably going to be circular. So if we know the cross-sectional area of the wire, we can use that to find the diameter. We are also not directly given the resistivity of copper, but we can look that up to find it 1.68 times 10 to the negative 8th ohm meters. Plugging in all those numbers, we find the area of our wires to be 3.4 times 10 to the negative 6 square meters. So now we can use this area to solve for the radius, which is of course half of the diameter, To find our wire needs to be 1.04 millimeters across. We can also look at the conductivity of material. Really, this is just the opposite of resistivity in that it describes how easily electrons are able to flow through a material. Conductivity is designated by the Greek symbol sigma and is simply the inverse of the material's resistivity. So if our resistivity decreases, then the conductivity increases. It makes sense because if the resistivity decreases, the resistance to the flow of electrons increases. This implies that the electrons are able to flow more freely through the material. So suppose we have a wire that has a total resistance of 1.2 ohms. Determine the conductivity of the wire if it has a diameter of 2.0 millimeters and a length of 30 meters. In order to find the conductivity, we have to know the resistivity. Since we don't know what type of wire, we can't just look that up. But we do know that we have a resistance and a length and some diameter of wire that we can use to find the area. So if we rearrange for resistivity, we can take the area times the resistance divided by the length, and we find 1.3 times 10 to the negative 7th ohm meters as our resistivity. Conductivity is the inverse of the resistivity, so all we have to do is take that and inverse it, and we find 8.0 times 10 to the 6th ohm meters inverse. So describing the resistance is a measure of how a device or material reduces the electric current flowing through it. One of the variables that determines resistance is resistivity, and this is specific to different materials. We can also use the conductivity, which is the inverse of the resistivity,